Let's continue our introduction to linear transformations and matrices. In this next video, we'll continue straight on from the last video. We had gone through two examples after our definition. One, the first, which was a linear transformation, and we verified that it was. The second was not a linear transformation, and we verified that as well. Now our next example, example 3. This time, let V be the vector space R2, and let W be the vector space P3. Remember, this is the vector space of all polynomials of degree less than or equal to 3. And I'll define a map F from V to W, and I'll define my map F like this. F will take the column vector with components A, B, and send it to the polynomial in P3, A t squared minus B. Now, this time I'll let you verify that F does preserve the vector space sum and the scalar multiplication of these vector spaces. So this F is, in fact, a linear map, but I'll leave the verification up to you. Our next example after that comes from taking V to be the vector space, which is the collection of all continuous functions on the interval a comma b, and for W we'll take the vector space R, or R1 if you'd like to think of it like that. Then here's a map from V to W. The map sends any function f to the integral of that function from a to b, and that is certainly a real number if you fix the interval a, b and evaluate this thing in a function. Great, so this is a map from V to W, and I'll go ahead and give it away again. This map is also a linear map. So 3 and 4 are two more examples of linear maps. And there are many more examples we could give, but we'll stop here. To continue, let's make this observation. Let L be a linear map from two vector spaces from vector space V to vector space W. Remember that every vector space has a zero element, in fact a unique zero element. So to keep things straight for our observation here, let's denote by 0 sub V the zero vector in V, and by 0 sub W the zero vector in W. Then we'll write down a few observations which almost seem that they don't bear mentioning because they're so obvious. The first one is that, of course, we can take the zero vector in V and write it as 0 plus 0. And what we'll do with that then is just take L of both sides. I'll take L of the left-hand side, L of the left-hand side and L of the right-hand side to obtain this expression right here. After all, if the left-hand side is equal to the right-hand side, then L of the left-hand side is equal to L of the right-hand side. And next, on the right-hand side, I will exploit or use the fact that L preserves vector sums. That is, that L of 0 plus 0 is equal to L of 0 plus L of 0. And so we obtain this. L of 0 is equal to L of 0 plus L of 0. Now what I'll do is I will subtract an L of 0 from each side of this equation. And when I do that, I'm just going to get 0 on the left-hand side. Of course, if this is the 0, not in V, but in the vector space W, I'll get 0W over here on the left-hand side. And on the right-hand side, well, of course, these two cancel out, and I'm left with one single L of 0V. So I've shown something that's worth mentioning and worth recording as a proposition or a theorem, that any linear map maps the zero vector to the zero vector. L of 0V must be equal to 0W. That is an important property which is used in a pretty important fashion in a lot of proofs. In hindsight, perhaps it seems obvious, but it is something that requires proof and is not listed as a property, but as a proposition. Now for our next observation, let's take two arbitrary vectors, U and V, in the vector space V. And now we'll record some more fairly obvious observations. The first is that, well, we can write V as V plus 0, and therefore L of V must be equal to L of V plus 0. But now, I'll zoom in on this, we'll take 0 and write it in a strange fashion. Here, this 0, I'm writing as negative u plus u. Now, it's true, right? 0 is equal to negative u plus u. It's true, and you should agree with me there, but then the question is, why would I ever write 0 in this fashion? It just looks more complicated than the thing that I began with. Well, the idea now is that I can apply the fact that L preserves vector sums and write this as L of v minus u plus L of u. So here the vector sum that I'm applying L to is the vector sum v minus u plus u. And so L must preserve that vector space sum. So now the thing I'm going to do is I'll subtract L of u from each side of this equality, over here on the left and over here on the right. Now, on the right, it just cancels out. But on the left, I'm left with something non-trivial. I'm left with L of v minus L of u. Now, if I just reverse the order in which these things appear on the equal sign, I obtain the following important property. I obtain the property that L of v minus u is L of v minus L of u. That is, L preserves not only vector sums, but vector differences as well. And again, this is a fact that may seem rather obvious in hindsight, but it is something we had to prove, and it is something that is quite useful in doing exercises and proving other important things. Now let's look at a pretty important example for the next big result. Here's our example. Take V to be the vector space R2 and W to be the vector space R3. Now, in R2, the vector space R2, we have the so-called standard basis. I call it the standard basis. What does your textbook call it? I think they call it the natural basis. Yeah, they call it the natural basis. So here's the standard or natural basis of R2. It's the vectors 1, 0, and 0, 1. I'll denote those vectors E1 and E0. Great. So now let's suppose that we have some linear map L. And I'm not going to tell you what it is. All I'm doing is telling you that we're assuming that it's linear. And let's suppose further that we don't know what L does on an arbitrary vector, but we do know what L does to these two basis vectors. We know that L maps E1 to 2, 3, negative 1, and L maps E2 to 0, 0, 2. I don't know why you wouldn't know what else L does except for the basis vectors, but that's the strange game we're playing for this example, that we are only given this information. Now, let's take an arbitrary vector in R2 that's not one of these basis vectors. Like, for example, 2, negative 4, this one right here. Now, my question is, what does L do to 2, negative 4? And your first answer should be, well, I don't know, because all I know is what L does to E1 and E2. I wasn't told what L does to an arbitrary vector. But let's look carefully at this expression. So 2, negative 4, we can write, as I've done in here, as a linear combination of the basis vectors. After all, they're basis vectors, and so I can write any vector as a linear combination of them. And so in particular, I can write 2, negative 4 as a linear combination. And the linear combination is pretty easy to figure out precisely because this is the natural basis. It's just 2e1 minus 4e2, which is what I've written down here. So to summarize, I've taken 2, negative 4, I've written it as a linear combination of the standard of the natural basis vectors, which is right here and right here. And now, important step, from here to here, I am using the fact that L preserves both vector sums and scalar multiples. First, I use the fact that I just obtained above, that since L preserves vector sums, it also preserves vector differences. So that L of 2e1 minus 4e2 is L of 2e1 minus L of 4e2. And then I pull those scalars 2 and 4 out, here and here, so that I get this thing right here. But now I have the vectors LE1 and LE2 sitting right here and here, and I know what those vectors are. Those are precisely 2, 3, -1 and 0, 0, 2. And so, in the last line, I can replace LE1 and LE2 with 2, 3, -1 and 0, 0, 2 as I've done here. And then just make this very quick vector calculation or matrix calculation to obtain 8, 2, -8. So what have I done? Somehow I have been able to reconstruct what L does to this vector 2, -4, even though in the very beginning I was only told what L does to these two natural basis vectors. Here we go from here all the way to here. So the phrase one hears in this context is the following. One says that L is completely determined by its action on the basis. That is, if we know how L acts on the basis, we can completely determine what L does to an arbitrary vector. Here's that moral written out. We can calculate any expression L of xy because essentially we do the same thing. We write xy as a linear combination of the basis vectors and then invoke the fact that L preserves both addition and scalar multiplication to write this thing as this thing. And again, the language one uses is often this. We say that L is completely determined by its action on this basis. Now, of course, there's nothing special about the natural basis we used here. We could have just as well specified what L does to any basis and then repeated this entire argument, writing the vector 2, -4 as a linear combination of arbitrary basis elements and arriving again at an answer. So there's nothing special about the standard basis. More generally, we can see from this example that if we fixed any basis of V, that L is completely determined by its action on a basis. We state this as a theorem. Let L be a linear map from V to W. Let V1 for Vk be a basis of V. Then L is completely determined by L of V1 through L of Vk. You'll have a chance to use this theorem in practice for some of the suggested exercises this week. For example, you'll be given a vector space and a basis, and you will be told what a linear transformation does to a basis, and you'll have to calculate what L does to an arbitrary vector. But I'll let you work on that, and then perhaps we can talk about some of the examples later.